one.
Yeah.
And I can't. Yeah. Me. Cool. Yeah. Okay.
The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. This is Tom O'Connor from DFR Solutions. I'm here with Ed Wyris, our presenter for today. Today promises to be a very interesting presentation on reliability of next-generation ICs, CPUs, GPUs, and FPGAs. You will find this to be a very fascinating and fast-moving discussion today. A little background on Ed. He has presented on wear-out behaviors in silicon and integrated circuit reliability to numerous companies and organizations, including the defense microelectronics activity, Boeing, Motorola, Ericsson, Xilinx, and various IPC, IEC, AEC, and MIL technical committees, and has over 25 publications on this topic. His current research includes characterizing transistor failure behavior of a range of technology nodes and device types. He's a member of IEEE, ASQ, the Electron Device Society, and the Association for Computing Machinery. His specialties include software security, computer-aided testing of complex integrated circuits, and electronic forensics analysis. Ed received his electrical engineering, computer engineering, and computer science degrees from Widener universities. With that, before I turn it over to Ed, we're all going to be keep everybody on silent mode. So if you have questions, there's a little box in the bottom that you can type in your questions, and we will take the questions and when we have appropriate breaks during the meeting or at the end of the meeting. With that, I would like to turn it over to Ed Wyris.
All right. Good morning, everyone. This presentation is a little fast-paced because of our time constraints. Questions, if you type them in, I'll try to get to them at the end of the presentation. If it's something that requires presentation to stop, then I can do some follow-ups after the fact if that's necessary. All right, so we're going to start with this. I'm going to be going over some semiconductor failure mechanisms, most notably the four provided on the outline slide, which are dielectric breakdown, electromigration, hot carrier effects, and negative bias temperature instability. All right, so we're going to go over a high-level discussion about what these mechanisms are and how they work, what thermo-electrical and physical conditions must be present in order for them to manifest, why these things are important, and what you can do about them as far as testing ICs against these mechanisms in order to have appropriate accelerated life tests in order to do life-limiting risk analyses on critical ICs within your circuits or systems. Okay, so to kind of jump right into this, a lot of times most people think that there are no issues with these ICs because there's no actual moving parts. But the fallacy is that there are moving parts, and they are the electrons that we have performed some level of alchemy on in order to get them to do what we need them to do in order to have these circuits, in fact, function. A lot of times we can misinterpret these failure signatures as EOS type of events or things that are extrinsically caused by external circuit conditions, transients on a bus line, or things of that nature. But a lot of these circuits can, in fact, fail due to inherent material properties, and we're going to go into some of those there. Okay. One of the main reasons why we are doing this is because there is no consistent response out in industry at any tier that we look at in the supply chain to say that who's responsible for guaranteeing that these devices are as reliable as we say they are, or as their data sheets say they are, such that our systems last as long as they need to, considering that these devices might be the life-limiting links. Okay, so go over it real fast. You know, a lot of presentations we do enlisted acronyms or definitions. I'm going to go through these real quickly so we're not hung up too much. So JDEC Publication 122 goes over in general form a lot of the failure modes from a physics standpoint that we go into for like physics of failure type of behaviors. We talk about dielectric breakdown and electromigrations and electrochemicals and things of that nature. So that's a good reference point for us to have in the industry. Different things that occur are faults, errors, instability, and failure. Primarily when we do accelerated testing, we talk about permanent faults or catastrophic failures. But what we need to consider in these appropriate life tests are that degradation can take place at some type of consumption rate. And that's what we want to focus on. Whether or not the IC will work as intended within the useful lifetime of our circuits. And if they stop working as intended, then the system may stop working, and that's what we're concerned about. Okay, so this goes into a little bit more of these definitions. Activation energy is typically 0.7 electron volts. This can change based on mechanisms, and we'll get into that too. Metastability has to do with a system staying in a state other than the system state of least energy for a long duration of time. This would be similar to having two clock domains within a circuit. One may or may not be a feedback loop. And if there are exceptions in the state diagram, then we could run the metastability issues. Okay. The acceleration models that we typically see are Arrhenius models, which have a strict temperature dependence, power law models, which have to do with natural phenomenon, and also the I-ring model, which has to do with a combination of those two. Some type of driving force. In these slides, we'll be talking about electric fields, and then temperature being another transitional force. Okay. So jump right in. We're looking at the MOSFET design in both planar and FinFET type of transistor layouts. Okay. So we know that electromigration takes place in metallization. We know that oxide breakdown takes place obviously in oxides. And then in the semiconductor region and the interfaces of it, which is our induction channel, we run into the issues of hot carrier effects, also bias temperature and stability. Okay. The first topic is dielectric breakdown. We're going to look at some failure signatures, some characteristics of this mechanism, and what they do on the circuit layout design stages in order to mitigate things of this nature. Okay. Provided here is an example of a dielectric breakdown site in a chip capacitor. Okay. It's very difficult to take images of dielectric breakdown events that are non-catastrophic when we're talking about ICs. The typical process is some large amount of electron microscopy with some focused ion beam milling in order to get into these localized sites of the ICs. Okay. So dielectric breakdown, for the most part, is electrical stress exceeding strength of the dielectric. It happens when valence band electrons escape and enter a quantum tunneling band, causing breakdown of the lattice. Okay. So a lot of the times this is talked about as an atomic diffusion type of process. A lot of the times we are kind of forced to have our focus on defect-driven mechanisms, where a defect is commonly referred to literally as that, as something that's within a material structure that we didn't intend to be there. Okay. Due to the circuit design and lithography and the actual buildup of these ICs, defects can also mean dislocations within the crystalline structure. It could be an air gap. It could be particulate matter. It could be a number of things, but they are still considered defects. And those defects, in whatever shape or form they're in, can migrate because of electric fields, stress relaxation, and those types of things. Okay. So what we typically say what happens is, due to an electric field over that oxide, The defects or the dislocations, as well as any trapped energized particles, can actually move through the interfaces of that dielectric. They can become trapped in the dielectric, or they can be trapped in regions along the dielectric. In any of these situations, what happens is the localized electric field in that area actually changes, which can impact the threshold voltage of the component, and it can also cause an increased amount of what we call stress-induced leakage current, or silk for short. Okay. If too much of this takes place, you actually have a conductive path aggregated between the semiconductor channel and a lot of the times the gate metallization of the gate structure, and that causes a shorting path. In that case, which is more catastrophic, the transistors will stop actually functioning. So it'll actually take a larger voltage to turn them on or off, or they may latch up. Okay, and this is due to a materials breakdown in that oxide. Okay, some of the electric models that we look at are typically the E model or the 1/E model, and these have to do with the kinetic energy necessary to move electrons outside of their bandpath regions. Okay, a lot of times we can actually bin a lot of different models against what we see with dielectric breakdown, but the important part is that we have to scale by the actual oxide thickness within the transistor. So for oxides that are thicker than 5 nanometer, which has to do roughly around the 110 nanometer node, thicker oxides usually follow the one model, thinner oxides follow another model, and then there's actual other models that we use when we change out the dielectric types and things like that. So there is some crossover, but we have to make sure that when we do in fact do our testing or our modeling, we're using the appropriate models, which have to do with the materials present and their sizes. Okay, so characteristics of the breakdown: the ideal field strength is usually about 30 megavolts per centimeter. Breakdown usually occurs well before that, and if there are defects present or the circuit has been laid out or manufactured with any deficiencies or marginalities, then that breakdown strength is actually even lower. Okay, so dielectric breakdown has a dependence on the electric field and or the voltage, which drives that electric field, temperature, and also oxide thickness. Those can correlate back and forth between each other, or we can focus on individual ones. Okay, a lot of times we like to use the electric field dependency models because those can actually be scaled better with our Moore's projections and things like that. Okay, the tunneling mechanisms taking place are actually Fowler-Nordheim tunneling model, which has to do with conduction band tunneling through a triangular barrier, and then there's also direct tunneling, where an even larger amount of energy must take place to transmit those electrons through those barriers. Okay, I'm not going into the details of these models because we have to assume that they take place. Fowler-Nordheim is actually used in flash memory to write to the floating gate, and some direct tunneling mechanisms are used in other types of flash memory or memory devices. Okay, the important things that we want to look at is this slide is going to talk about voltages. The following one is going to talk about electric fields. Okay, so as far as dependencies go, if you've got thin oxides, which are nodes less than 110 nanometer, there's voltage independence on the thickness. Greater than that, we see a dependence on thickness. The driving factor here is the scaling that they've done over time has kind of plateaued in a sense, where the supply voltage on the component is still about the same that it was at the previous node, but the thickness of the oxides decreased such that the electric field has skyrocketed. Okay, so as they scale down, those voltages will remain the same, showing some overlap in these, in the top part of these trends here. So your 2 and 3 nanometer, as the slide shows. When we look at electric fields, on the other hand, it's the same type of thing, where the thinner you go, because the thickness has changed, the voltages remain constant, you actually see an increase in these electric fields. Okay, versus the thick oxides where the scaling is less dependent on that. Okay? Some of the trade-offs they do on the design side is they can actually change some of the gate capacitance between circuit elements. They can change the width of the metal, size of the gates, and these types of things. So these are physical design changes of the layout of the IC. And they can actually modify those in such a way that they can mitigate dielectric breakdown. And this assumes that no defects show up during the lithography steps of making the device. But this shows that in the design verification steps, we can actually push back the life of the product and increase it in some cases. Okay, go into electromigration a little bit here. The failure of this is primarily when an electric field exists over a metal line. The electrons in it actually bombard grain boundaries and triple points, which cause the metal atoms to actually move, physically move out of place. So in some regions, you can actually have metal extrusions, and we call those hillocks. In other places, we have metal voids show up. The matter's got to come from somewhere. So it ends up coming from the top of a stream and ends up going down a stream, or it ends up getting stuck in corners and things like that. Okay. So what's happened is, due to the physical reduction of the transistor sizes, they're ending up with higher current densities within these metal lines, and that is causing an increased effectiveness to happen. It is being seen worse in vias and things like that than in the metal lines of the traces on die. So the issue is that between the layers and the different layers in the metallization, as we go smaller and smaller, we will induce interconnect voids between those metal lines, causing the overall IC to stop working. And it could be as few as a handful of atoms, or it could just be a landslide phenomena, and we can void out a whole metal trace. And we've seen both in the labs here at DFR. Okay. So the model for that was developed actually back in the late 60s, and they've got a good grasp on this. It's actually a Black's electromigration lifetime equation, where they can look at the 3D geometry of the volume of a metal line, and then also look at the deposited metallization structure within those traces. And you can have a good rule of thumb and predict when those traces will fail. Some of this is actually implemented in some industry spreadsheet coding that we do for lifetime modeling, lifetime predictions for electromigration structures and things like that. Okay, so for design verification, similar things that they do for dielectric breakdown, it's all about geometries here. If there are any right angle turns, then you actually have pitch points and current crowding takes place. In other situations, you have the absence of current crowding, which means your current's going to be somewhere else that you don't want it to be. Changing up the metal and the conductive properties of these metals, so you can actually do more alloying. We can push back the time it takes for electromigration to manifest. Aluminum takes place sooner, copper takes place later, but we know from some of our packaging studies and our wire bonding studies that we've introduced more issues when we've switched over to copper wire bonds. So we can't just switch out what materials we're using in these chemistries, thinking that we can eliminate one thing, but we're robbing Peter to pay Paul, and we're going to introduce other more dominant mechanisms, which will cause failure to our circuits sooner than these would. Okay, hot carrier effects is actually a more of a detailed study that you could go into, and we could spend days talking about it, but we're not going to, luckily. And mainly this is degradation of voltage parameters on die. So a lot of the times what we see is parametric shifts taking place with a threshold voltage, leakage current, and capacitance. While this may not cause a catastrophic failure, it can cause a system instability and system downtime. As far as, let's say that some of the data that we've seen for this affects circuits and ICs up to the quarter micron node, or 250 nanometers. where what will happen is we'll have hotspots generated in places, and other areas will have transistors that can't switch because the electric fields are off from what they were intended to be. Okay. So what happens here is when you apply a drain bias to a transistor, what happens is the gate turns on your transistor, and the current goes from source to drain, or drain to source. However, you have your bias set up on it, and however the device is set up, and what bounds and what regions. But in all actuality, you're energizing through kinetic energy the electrons within that conducting channel or on the ends of it. And as they become energized and your channel opens, which allows those electrons to go across, that's your induced current, the electric fields that are generated actually steer the electrons into other areas. And due to some of the collisions that take place and the stacking of those electric fields, you can actually steer the electrons to go to places where you don't want them to. The other part of this is, which makes hot carrier effects worse, is that it actually has an inverse activation energy. So it's a negative number. So in times where we're actually not testing devices or our systems at lower temperatures, we're all familiar with doing a high temperature operating life test. In those tests, you won't manifest hot carrier effects unless it's going to be a random effect. You can actually get these to manifest when you test at lower temperatures, room temperature and below. There are times where we've done some testing at -25 or -35 C as a die temperature, and we've gotten actually good behavior that fits these hot carrier models where we've caused things on die to fail. And I'll talk about some of that later on in the presentation here. So hot carrier effects, here's a little image I put together for presentation a few years ago, which gives you more of a visual aid here to understand what's going on. In the next slide, we're going to go into what A, B, C, and D are. So just stare at this for a moment, memorize it, and we'll move on. So in A, we have hot carriers are created when there is a bias on the gate that creates an induced current path. Under these conditions, it's probable for a carrier to gain excess energy. So it's all about probabilities at this point and working with workflow functions to define what the energy carriers are and things like that. So that's his first part over here. So going on to B, some carriers do lose energy. Others can gain sufficient energy due to collisions to overcome energy barriers. So they end up actually getting out of that semiconductor region and entering oxides, or they enter the interface regions and get trapped there. Okay. So we've got C, the region for C as well. That would be injection into an oxide. Okay. At some points in time, when you do have an energized carrier, you can, at some point in time, through the distance it travels, which needs to be a free mean path distance, it will lose energy over time and distance, or also lose energy due to collisions, and they will recombine or come out of the conduction band and back in the valence band and lose that energy and just kind of annihilate themselves. Okay, we're going to go into more of that one, a little bit of detail. So to talk about A here, the carrier is lucky. That's why we call some of these mechanism models the lucky electron model. It's based on probabilities and things like that. So what happens is that lucky carrier gains enough energy to escape its bounds. Okay, so after its momentum is redirected and the angle has changed, it will reach an interface. And if it does still have energy left, it will overcome that interface or be reflected by it if there's not enough energy present. Okay. For impact ionization, this looks at our energy bands, so the valence band and the conduction band. We know that if there's enough energy, you can escape the valence band. If enough energy is lost, you can jump out of the conduction band. And it's all about what we've done with dopings and things like that in those channels. Okay. As far as energy barriers go, here's a good textbook example of that, looking at the interface difference between silicon and silicon dioxide, but the energy that must be overcome in order to either be reflected, tunneled, or transmitted across those barriers. Okay? Going to D, this carrier pair recombination, it's a twofold model. One has to do with the energy space, which we've We've talked about a little bit of conduction and valence. The other has to do with real space. So if the electron and the hole are not near each other physically, they're not going to recombine, even if the energy exchange takes place. Okay, they'll just keep occurring. This, reaction, diffusion reaction model type of cyclic redundancy that's taking place. When we do modeling for hot carrier effects, this typically isn't done with a time to failure type of thing. It's more of a time to when it will affect a parameter. Okay, so a lot of times in circuit models, we'll build out our equivalent circuitry and things like that, whether it's equivalent for a function, equivalence for impedance, or something of that nature. What we do know, when a transistor degrades, it will be affected in either its threshold voltage or one of the current parameters will be affected. And we know that we can increase or decrease those with some time-dependent variable. So that allows us to do reliability simulation models, or age modeling, which allows us to recursively call up a function and then output, will our circuit still work within bounds as intended while these transistors degrade? At some point in time with degradation, at some time coefficient, we know that those conditions will be met and our circuit should stop working. So if we can compare real-life situations to these models through age simulation, then we're actually able to do some type of good enough predictions using that. The issue is a lot of the times with end-user devices, we don't have enough insight into how these circuits are put together without doing some level of reverse engineering in order to see truly which transistors are affected and how the design was modified in order to account for these age parameters. Okay. So next one is negative bias temperature and stability. Same type of things that we'll talk about. Degradation here is also based on device performance, so a voltage parameter that's going to change. This one notably is the threshold voltage on the component, and that will increase as things change. Okay, so this happens when ever there's a time that a gate bias takes place, whether you're going to switch on or off a transistor, you're going to hold it in some half state, it doesn't really matter as long as that gate bias is present. So what will happen is it's kind of like, if you think of it as a precipitation evaporation type of event taking place in our macro world. What happens is the electrons will leave the conducting channel, and they will actually knock out some of the pacified silicon hydrogen bonds that are along that interface, and that will in turn cause your electric field to change. If it changes enough in certain regions, then your device can not turn on or it can latch up and not turn off, and things of that nature. A lot of times we don't talk about positive bias temperature and stability. I mentioned a good note here, because a lot of times that's recoverable with different toggling that you can do on transistors. Some of the FPGAs actually do a type of underlying system check where they can toggle some of the PMOS pairs, which can reset this mechanism, which is good, but if your device is going to stop working after a certain percentage, toggling is not going to help for those situations. So as I mentioned before, this breaks silicon hydrogen interface bonds, and it does in fact recover itself. So in all of our devices, this type of mechanism is taking place, but it may not take place enough where it's going to affect us or affect our system performance. Okay. So we did the case study here at DFR with some of the aerospace companies where we looked at an ASIC. This ASIC was set up as a different arrays of PMOS, NMOS transistors, and also a low noise amplifier and some other things. So what we did was we were able to do some gate measurements and some current measurements and do some stressing of applied voltage, and then go back and read back some of these parameters. And we found that over time you actually do see a shift in these parameters. But then also at the same time, at some point in time, you'll have a plateau effect take place. So we believe, as far as literature searches goes and what we can speculate based on the test results, that at some point in time you either run out of places where you can have traps take place, or enough of them recover. So you do plateau. So one good thing that we must point out here would be bullet point 3. The device that we looked at had about an 8.5% degradation. That was the maximum it could shift away from what our nominal voltages were. Okay. If the device was spec'd at a plus or minus 5%, then you would see an issue within the useful life of your product. If your device was spec'd at a plus or minus 10%, then this becomes a moot point. But these are the things you've got to consider when doing a life-limiting analysis on a part. It may not be an issue, but at times it can be, and it can be devastating to your system. Okay, so the same thing that went on with hot carrier effects, you do the same type of age modeling within those circuits. Once again, you can't really do this on the device stage because you don't have insight into those circuit models and things like that. And while there's a lot of different models for hot carrier effects, there's actually only 1 or 2 models for NBTI, and we usually just look at a power model for that. Okay. So to go a little bit away from what those intrinsic mechanisms were, here's a little bit of extrinsic. So things that we can accidentally cause to a circuit, either based on the manufacturing of it, we did a step wrong, or we induced something due to use, okay, which will cause problems. I don't think this slide deck talks about radiation effects, but I did want to cause that out. That happens in our atmosphere and also in space. And it's all randomized, and there's a lot of data on different types of particles that can cause it to occur. But a lot of times EOS has to do with handling mistakes, testing mistakes, or improper use, or it has to do with some type of voltage protection that didn't quite do its job. So you can get a transient voltage spike on a line that's several hundred times more than what nominal should be. Several orders of magnitude. And other times, maybe that won't happen, but it's still a concern here. So here are some of the images that I sourced from online. Unfortunately, I can't provide pictures from any of our lab work due to customer NDAs and things like that. But these are good examples. So EOS, if it's hit with a short enough pulse, you can blow holes in things. If it's a low energy pulse, but it takes place over a longer amount of time, you can cause metallization to melt. You can cause ruptures of dielectric that are present and things like that. So these are those low sources. Okay. ESD, on the other hand, would be a fast spike, but based on humidity conditions out here on our floor, you can actually cause much more damage than an EOS event because of the energy associated with those spikes. I'll put a little chart in here about different things that take place in handling and what the associated voltage ranges would be with that. And you can see how it differs between 10 and 50% relative humidity. And the spike differences are huge. I mean, just example that second one there, the motion of a bench employee. So that's somebody sitting at a desk moving back and forth, something like that. At 10% relative humidity, you're about 6,000 volts. At 50%, you're at 400. So huge differences in handling, and some people don't think about the controls that they need on the floor. Okay, ESD type of damages can look like our intrinsic mechanisms, but based on the location and actually the experience of the person looking for them, you can easily discern between them. Okay, so here's some more examples of ESD-related punctures and things like that. Okay, stress migration, on the other hand, has to do with stress relaxation and the exchange of where those stresses must go after manufacturing has taken place. Okay, good instances are on package scale things. We look at underfill and things like that, where if your temperature goes through the glass transition phase or glass transition temperature of the underfill, then you can have a phase change take place from solid to a semi-expanding goop, and then back down to a solid and things like that. So you have some of these stress concentrations take place, and it needs to be relaxed into something. So what we see is we have non-electromigration style voiding that takes place. You usually see wedges or triangles. Electromigration, on the other hand, you would see missing material in one place and that material showing up somewhere down the line. Usually that occurs in one direction as opposed to coming in like a mouse bite on the side of a line. At other times, you can have a lot of metallization in the region will actually delaminate itself. or delaminate onto other metallization. And here are some images of that too. Okay. So what can we do with all this information? While we've only talked about it in such a high level, we could go into the nitty-gritty details. But we have to think to ourselves, well, what's the point? How can we actually benefit from doing this type of analysis? So a lot of times what we do is we say, okay, we want to investigate the reliability of our ICs. Let's turn to MIL-217 or a Telcordia reliability prediction methodology and things like that. And there's a number of them out there that we have now in industry. But the one that everyone seems to go back to is MIL Handbook 217. Wanted to include this slide in here just as a means of we've gone beyond this in some places in industry by trying to assess things more accurately in order to show that they are more representative and test to what we see in the field. Okay. So what we need to do is we need to find this happy medium point. So a lot of the research that I've done has gone into putting together a set of algorithms and a procedures or methodology in order to investigate the reliability of these ICs to make it actually more value than just a standard strict MTBF number, where that would be like 1 fit or 2 fit, suggesting that the device will last for 1 billion years, or it should never ever fall or fail. And it doesn't matter what type of device it is. If you run it in an HTOL test for the same amount of time, it's going to have the same failure rate, and there's no escaping that. That's just how the math plays out each and every time. Okay. So what we want to be able to do is use some physical data about a device. The layout of it, the materials that are present, the technology node, and then the device functionality itself, and use that information in order to build up a metric to determine what the device reliability is based on use conditions. So we believe we've actually done that, and we're in the process of actually making it from our development code into production code. I'm going to walk through some of these steps here. Okay. So the scope of the work was to develop some predictive models that we can use for a whole lot of different integrated circuits, CPUs, GPUs, different types of memories, different microcontrollers, everything that's out there while trying to stick with a common library. Okay, so we're between phase 2 and phase 3 of this kind of scope of work for this analysis type. Okay, so what we were tasked to do a few years ago for the aerospace industry, with a number of companies supporting a group called AVSI, or the Aerospace Vehicle Systems Institute, we were tasked to develop these types of algorithms so that anybody in an OEM who needed to study the reliability of a part could actually go in and use some high-level commands or selections in order to do just that, without needing to know too much of the proprietary details or any of the proprietary details of a component that they're trying to investigate, which we all know a lot of that is highly confidential and you'll never get. Okay, so the challenges are always what type of information is present, whom can we call to get that if we don't have a friend inside. Okay, so the MTBF methods typically rely on a number of transistors, or maybe the number of bits of a device, or maybe the number of pins sticking out the bottom of it. Well, what we're trying to do is focus more so on what's on that die itself. Okay, because these are how those fail. And if we need to build in package models, we can do that too. Sherlock does a lot of that, and that's our board-level design analysis tool here at DFR. So the reference material that we typically have is technology node, materials, and a description of pretty much what it does. Other things we can obtain, we can decapsulate a device or delete it. We can take a picture of the die. We can do some optical and thermal imaging to figure out exactly what's there, or some rule of thumbs as far as how many circuit elements might be present. Okay, so here's the vertical flow of this algorithm. It allows us to model the simultaneous degradation behavior of multiple mechanisms that we can assess for any part. Okay, and that allows us to actually do a good prediction that can be used in a number of different things. So you can use it in an MTBF analysis if you need to. You can use it in when you use fishbone diagrams. You can use it in just your high-level life-limiting assessment or an identification of critical components and things like that. Actually determine what you need. Here's the horizontal workflow, which allows you to actually see more of the breakdown of what we're able to do in the different levels. So if you don't have much information about a device, we can take a high-level approach, take some assumptions, take some approximations, use some information from literature. We don't really feel like doing much. Use our HTOL conditions, and then do our trade-offs and our calculations, and we can actually output a decent number. And we've got a few publications which shows how good those guesses actually are using those assumptions, and we've got some field return data which we've based that off of, where we fall within a plus or minus 20% window as far as how many orders of magnitude off are we from those predictions. If we've got manufacturer's info, we can actually break out into IP blocks, use some in-house review data for those transistors. We can use some equations and coefficients that are provided from the fabs with foundries, use some conditions, and then also go through it and calculate device reliability. Or we can do it as a black box approach, which some of these slides we'll talk about later on, about treating it as a single DUT, looking at it from a benchmarking and stress testing perspective to see what our actual margins are outside of guard banding, what can we do to the device to see how to stress it, and then how we stress it and what fails and what degrades, and then use that information to do trade-offs and a reliability prediction. Okay. So life-limiting analysis. Seems that a lot of standards and guideline documents are starting to include physics of failure type of documentation or mentions or references. Okay. And this has been taking place over the past few years. And these are just some examples here. So what we're going to talk about a little bit is what you would do in performing a life-limiting analysis. Okay. So that's what this little flow chart shows, that you've got information from a number of different places. You may have a complete set of data. You may have an incomplete set of data or no data at all. You have your requirements from the OEM you're working with, and you know what the industry's best practices are. So what we can actually do is we can go through these steps and we can do a traditional MTBF. We can do the MIL 217, Telcordia, any issue with that, 1, 2, or 3. We can do FIDUS. And we can do the one I always forget, it's the IEC 62 something. For a life-limiting analysis, same type of thing. We can go through these and look at the mechanism susceptibility, acceleration transforms, do component life testing. In both cases, we can apply a usage profile. So we know that sitting in the Arizona desert heat, we're not going to see 110 degrees Celsius all the time. It's going to be binned and it's going to fluctuate. But you can actually apply those mission profiles, so to speak, to these types of analyses before you calculate out the lifetime. It gives a more accurate, for MTBF, it's a more accurate way of presenting results than saying that it's in an air conditioning controlled building without humidity, without human contact or control, and we just count it as ground benign, where it's rarely the case for that, but that gives us our lowest multipliers. Okay. We do some reporting. Okay. We go through some of these steps here with for this methodology using the we're going to talk about in the presentation. So ASIC, for instance. We can look at an ASIC based on a functional group methodology. So if we look at it for high-end assessment, it's got a layout, device symbols off a schematic, equivalent design. We know that a low-noise amplifier, this case study, behaves in such a way. We know that a mixer behaves in such a way. We know that a VCO behaves in such a way. We've actually built up PLLs and things like that in SPICE programs and do these simulations on before we actually do the actual testing. Okay, to make sure that we can correlate the different types of that horizontal approach. So a high level to more info to a black box type of thing. Okay, so we look at accelerated conditions. This is from that NBTI ASIC test, or it's as simple as we know the conditions were based off of MIL standard 883. We know what our stress value and our nominal field value is, and based on that, we can plot some data, do our test. We know that we're going to use a time power law model for this mechanism, and then using that, it actually goes into how the calculations performed. And a lot of us are familiar with this. It's just a standard acceleration transform equation that we can hit against. And we know that we can do, if we've got a failure rate under test, whether that's a legitimate test or not, that's meant for those HTOLs against hot carrier effects. And then we can correlate back to use conditions using our usage profile. Okay. So for complex integrated circuits as far as CPUs, what I'm going to do is walk you through one of the case studies we've done in the last 6 to 8 months. This was on Intel CPUs. So we took a look at the 22 nanometer FinFET designs. Those are those 3D gate structures in these transistors. We've scaled down so far that there's not enough of an effective electric field over the induction channel. So if we add a fin around it, or top and sides, then the cumulative sum of those electric fields is enough to get those electrons flowing. Okay. So a lot of times when we buy these off-the-shelf devices, there's not much guidance with it. We know that we should operate it in a benign environment. We know that it should last between maybe 3 to 5 years because it's a consumer-grade product, and we expect something better is going to come along the lines. But what if we want to have a high reliability application and put higher performance parts in it, such as this, and use it outside of those margins? Okay, so how can we do stuff like that? Well, what we need to do is develop a test in order to literally stress the component 100% of the time in every which way possible. So a lot of times what we do here is, if it's a GPU-based test, we try to do some type of graphics burn-in profile on it. If it's a CPU-based test, what we want to do is get that CPU to work at it really, really hard without having it actually turn on some of its advanced functionality. And this is actually, I'm going to call out the that little weightlifting body workout type of thing, or P90X, where they say that if you keep mixing up each type of activity you're doing, you won't give your body time, or in this case, the IC time, to compensate. Okay, so we can do this in a matter of polynomial arithmetic, different state models, as you can do with the folding at home group out of Stanford, or we can do different types of rendering. Maybe we calculate pi out to 1 billion decimal places or something like that. Different things that you do can actually enable different things on those processors, some which maybe you want to stress, maybe you don't. It really depends on what your application is and setting up the test to match your application. Okay, so if you're doing test monitoring, we need to have some type of arbitration circuit set up outside of your DUTs. DUTs here would be our CPUs on different platforms. You can modify your DUT in order to actually have the temperature that you need to on die. What we're trying to do is not stress the solder joints on the motherboards of these circuit cards. We just want to stress the CPU die itself. In the same case with the ASICs or GPUs or FPGAs. We're looking at just that die causing things to fail. Okay, so we want to do some type of health monitoring as well. And you can decide what that needs to be. In this case, it was whether or not the computer responded to network commands, making sure that it was still doing what it needed to be doing with parent and child threads and software. Okay, so we did accelerating testing in a two-corner type test due to some of our resource constraints for a customer that we had. And we tested the CPUs at 65 C die temp and negative 25 C die temp, running at a clock frequency higher than what the factory clock was set to. So in this case, it was about 1 gigahertz higher than was intended for the device. It's worth noting that 4.4 gigahertz was not the maximum clock speed we could run these at. We had them actually running at about 6.5 gigahertz, so we know that there is sufficient guard band above that for us to work with and a good enough safety factor. Okay, so we went ahead and we ran these, and the goal was to run them for about 9 months and see what we could actually uncover. So it's worth noting for the model creation on this that through a lot of papers that we were able to find that there was no new failure mechanisms introduced, and the classic models for, say, dielectric breakdown or hot carrier effects, which exist for the planar transistors, actually also take place in these FinFET designs. Okay, so for this we tracked threshold voltage and core voltage of the CPU at like 30-second intervals for 4 to 9 months. Okay, at about 11 weeks we had actually cascading failures for the parts running at cold temperature. Here's some of that data. So we can actually use time to failure data and some median rank estimations to come up with our beta value for Weibel, our characteristic life or eta, and also our our power gamma coefficient, which would be the best fit lines exponential function there, or it's the x to whatever power is that gamma. Okay, this right here. So this type of Excel spreadsheet analysis can be done. No other fancy software is necessary, so literally all of us can be doing this. Okay, low-cost testing. It's important to assess this reliability. Okay, here's a data plot in a different way, using the temperature coefficient and the voltage coefficient for these accelerator transforms. As you can see, while we do have that one fit that we all experience or we see in these MTBF analyses, at about it's about a year of constant operating use. Just beyond that, we actually have an exponential rise of failure rate on these devices. It's worth noting that each and every one of these systems, while we tried to make it as closely fitting for lot-to-lot part sourcing, we had all independent systems running on different power conditioners, different UPSs, using screened memory and all this other stuff. And it was funny to see that actually we had 4 fail within days of each other in a given week. The 5th system didn't fail. That actually continued to go through. So that's that data there. Okay. So the next part about this was interesting. FPGAs. Can we do the same type of testing knowing full well that we've got to program these devices first? Well, the answer is yes. So our motivation was to kind of work with the NASA supply chain and those guys over at NASA to look at space-bound systems. And a lot of the times they're using older technology because we've got plenty of empirical data on it, both in the lab and in the field, in order to determine what the reliability of these parts are. The problem is they're becoming obsolete. So what do? Do we go to the next generation, which may also be obsolete in the next few years, or do we use the latest and the greatest out of a supplier based on not much data? I don't want to say no data, but not much data. So we know that the 3D packages introduced in these Vertex 7 series may introduce new issues with the through-silicon vias and that stacked die, okay, or even the 28 nanometer feature size, which was a few years ago, and again, cutting edge. Okay, so the activity primarily looks at the fact that we must program these devices in such a way, and with all our companies, we like to use code repositories and things like that. And if we do that in a certain way, can we track code in order to determine if a device is degrading? Okay. In this case, we could look at a feedback loop or unfeedback loop with the time it takes to do mathematical processing. So some given time associated with the loop, and then seeing how that changes over time. So we did similar to the CPU test. We took some evaluation cards, and we wanted to just mess with the FPGA on it. So what we did was we modified the thermal solution. For the high temperature exposure, we literally just put these in a heating chamber, convection airflow, 100 degrees Celsius. For the cold side, we build up a water block and chiller stack up, and then actually build a chamber around that, using things we had laying around in the lab, of course, as you can see in the image. But it still works. Okay, so whether or not you use a $15,000 chamber or you build up one for under $1,000, the goal is still the same, to have a worthwhile environment that's accurate to do testing with. So in this case, the ambient air in that box was negative 65 Celsius. The die temp itself was negative 35, okay, which is what we were aiming for. Okay, and we were actually able to find anomalous events based on communication that was all one direction, solely based on the DSP program block on die, from inside of that FPGA back to a receiving computer that was expecting to receive a $sign every 2.8 seconds. Okay. At times, it didn't receive it within the amount of time. Sometimes we saw it speed up. Sometimes we saw it slow down, which kind of shows here in this positive versus negative receipt of these events. And while the number of events aren't off the chart, we're looking at, for the cold systems, we had 11 and 15. For the hot systems, 17 and 1. Not too many, but this still shows that some system instability takes place at the ends of the operating margins for this component. It wasn't actually the RTX 7 platform. It's lower cost, lower amount of I/O. Still the same fab process to develop these components. Okay. So the model creation, same type of thing. This just shows how many events we had cumulative-wise proceeding over time. We believe this has to do with negative bias temperature instability. Some failure analysis is taking place to see what's going on with that. We didn't fill out this model for NBTI. We were actually looking for dielectric breakdown failures and hot carrier effects. So if we do go back and look at this, the math and the data, that we'll probably pair it to this NBTI model, and I'm sure it'll fit. Okay, so to kind of go into how we can apply this. These are some screenshots from an earlier version of our IC wear-out tool that we developed. Primarily, this gives you a very high-level approach if you were to do those functional group breakdown and probability of a failure of your system if you have some parametric breakdown or parametric failure of any functional group within that IC. So this kind of looks at different things from ADCs or memory structures into some low-level gate logic into transistors for bigger devices. So we did build up a PLL that was like 5,000 transistors plus. We have multiplexers, VCOs, and things of that nature. Okay. While in this screenshot it shows that we only have one node size pick, I've got a version of this in spreadsheet form where we can actually split different node size for the different functional groups and things like that, or you can build up your own functional block from equivalent circuitry. Okay, you can put in some testing information here, select confidence level, then also pick a mission type of profile. We expect a lot of the complex ICs to have different operating states, whether that's a low power state, a fully on operating state, maybe a turbo state, as we saw with some of the earlier Pentiums many years ago. And we know that the temperature does change, the voltage may change as well. So we wanted to make sure we addressed that in this type of operational workflow. Okay. And then what does come out of this is a time-dependent characterization showing what the reliability of the device is and what the failure rate is. And these are just two examples from a no-name microcontroller. So we can check we do have the same information that you can use in your other analyses that are already taking place. Okay. And I believe that I was fast enough to go through this that there is some time for questions.
First question we have, is there an evaluation version of the IC wear-out tool available from DFR?
I believe, as far as that question goes, there is an evaluation version. It is not the latest and the greatest that I've worked on, but there is, it does do enough things to allow you to assess some ICs. And that would be, we've actually went through and we did an analysis of a Vertex 4 FPGA using that tool, as well as a number of other ICs, some analog to digital converters, some DRAM and SRAM devices. While this is good for a lot of complex ICs, it's not good for things like, say, a simple little voltage regulator or one single FET device. You can use it for that, but if you're using your FET device with proper derating, it may not be a worthwhile adventure to just do this. Okay, as long as you've done those other checks and balances for your system, you should be okay with those simple things.
That's the only question I have right now. Over here, we do have the ability, you can raise your hand. I can look for you and see if you've raised your hand, and we can unmute you. So at that point, if you have a question that you would like to ask, raise your hand. I'm scrolling through here to see if I have any hands raised. If not, I know we have passed the bewitching hour, which is the lunch hour, 12 noon here. And people are starting to leave for their lunch breaks. And I don't see any questions.
Well, the slide deck I'm pretty sure is going to be available on our website after today. I have a variety of different papers and publications that go with some of these slides. I know a few of those are available on our website. I've got other ones that I can send out, most notably that document that goes with the FPGA assessment that we did in the testing, as well as the one for the Intel CPUs.
Okay, we are starting to get a couple of questions in. First question here is from Anastasio. How much can you trust the results of the information from the OCM? Is it limited?
Okay. We actually did a study for components at 130 nanometer and 90 nanometer. And we worked with some gentlemen out of one of the Motorola divisions for this. And we had information from about, I believe it was 9 years worth of component tracking all the way down to what failed on assembly, whether it was an IC due to a solder joint or an IC due to an unknown failure, and what the conditions were and things like that. And our numbers were actually pretty good. They were within an order of magnitude, so no error bars that were twice what the failure rates were and things like that. Some of the other information we've actually been able to compare after the fact with the predictions we've done to then a test after the fact or field return data after the fact as follow-up for some of the consulting work that we've done. So it really depends on what you need to get out of this type of assessment as well. So if you're just looking for a standard MTBF number, I challenge you to use our tool and see how that compares with the handbooks. You may get a better number, you may get a worse. If the reason you're doing an MTBF is due to kind of, I guess, VC money or marketing value or something along those lines, then you may want to stick with the handbook. But if you're trying to do this to see when your system may fail, your IC may fail, go ahead and use our tool. Find one like it. I know there's some companies are doing this in-house. Some organizations out there have similar tools using similar models. But I think it's important to come at it from both sides. And this is for things that if you're looking at higher reliability, so I'm not talking, if your device is only going to last a year, your system is, maybe this isn't that big of a deal, but if you're looking for 7 to 10 years or longer, say high reliability 30 years plus, then you're going to want to know when these devices are going to fail. And if they're going to fail within your useful life, and if that means you're going to replace your circuit card, if you're going to repair it, or you got to throw the whole thing out because it catastrophically failed, that's something everyone's going to have to figure out to some extent.
Ki-Lu, have you done this on consumer electronics?
I've done this on extended and industrial range electronics, and we've done this also on consumer electronics. I think we've actually hit all ends of the spectrum. So the ASIC was for a high reliability space application. Some of the testing that we've done for the FPGAs and some of these other ICs, which we didn't talk about before, extended to industrial range electronics. So like -40, -55 to 80 for 125 source operating ranges go. And then we've done a handful of consumer electronics. A lot of the times, those we don't leverage resources too well.
Mark has a question. What is the password for your online reliability calculator?
Okay. The password actually has to do with individual user accounts. So send in a request for more information off of the contact us form there, or shoot me an email, then I can get you a password. Well, user account and password. And then the only requirement for that is to have a latest version of Java installed.
Okay. The next question comes from Yasir. How efficiently could test for effect of VSD-based failures in CMOS-based ICs, i.e. CMOS latching?
Okay. The issue with testing for ESD, a lot of times we take a test rig, whether that's built up or it's a handheld device, and we shock the device in some type of fashion, whether that's hit all the pins, hit a pin at a time, ground the device in a variety of different ways, and base that off of the different models. I think we've got now the charged device model, or CDM, and the human body model. I think industry has kind of thrown away the machine model because it really doesn't happen. The problem with that is you can cause devices to be walking wounded if they don't have good enough voltage protection on them or fast transient protection and things like that. So if you're doing that type of testing, a lot of times that's not long duration testing. When I say that, I mean a test longer than 1,000 hours. Most time we truncate our test at 1,000 hours. I'm suggesting that you test for 2,000 or 2,500 hours out to 4,000 hours. And while that's longer, that's usually the time it takes around the 2,500 hour point is when the degradation behavior starts taking place. So the ESD test may not give you the same behavior, either recorded out over time like in situ, or may not be the same type of failure mode.
Okay, one last question. Oh, I got two more questions here. Ed, from Jim Keebler. Ed's slides mention MTBF and its relationship to reliability analysis and Mill Handbook 217. Does Mill Handbook 217 define MTBF as did Mill Standard 721C at one time, which was deleted in 1995?
Well, from our experience here, a lot of the times MTBF is used as the de facto reliability metric for our components, a circuit board, and that type of thing. We've done a lot of critical component analysis. We've done a lot of aggregate modeling and things like that using our Sherlock tool and our standard design review processes that we've done here. The problem is, and I guess I can see if I can run back up to this slide here. Okay, that slide. So while this memo here out of the Army states that we shouldn't use 217, 217 is the go-to handbook. We get requests in here all the time to do that type of thing. And I know information coming out when we find the component having an issue, a lot of the times we're told, hey, but MIL 217 said it was this. And that's based off of empirical data from the early 90s and late 80s, which may not be applicable to today's technology. As I kind of mentioned in, let's see, it's in this, sorry, I'm just flipping back and forth here. For the slides that talked about what the life-limiting analysis would be, to look at the different circuits within a device or an assembly. So we'd go down a bomb, similar to a bomb scrub, and we would look at the different components and the placement, the physical placement of those components on the board, maybe plating mismatch, CTE mismatches from package to board, layers in between boards, temperatures you're running parts at versus what the types of parts are, like aluminum electrolytics or something of that nature. So it depends on what your requirements are, really. That's really what it comes down to. If VITA 51.2 is what you're using, that says to use physics of failure. If you're going to use the latest draft of MIL 217, it states just use that, but stick within its bounds and constraints. If you've got just a MIL 217 or a Telcordia type of requirement, that's really up to you and what you're allowed to do to assess the reliability. But all I can say is hindsight isn't our friend a lot of the time when it comes to this. So whether it gives you a warm and fuzzy now to say that your numbers are low and it's good and your product will last 100,000 years, in reality, my gut says it won't, and your gut may say that you want to cover your bases. So maybe doing a checks and balances using something else could be helpful.
Okay, we have one follow-up on that question. Does 217 Plus include any physics of failure?
217 Plus does not, as far as all my utilizations of it. So 217 Plus, as far as I know, only includes a difference of some of the lookup tables within it. Well, within 217 itself were updated or scaled accordingly through extrapolation. And then there's some audit questions, as I like to call them. They're similar to the audit questions that are in the FIDUS handbook, which goes through how to do that MTBF, and that's usually like a quality and reliability check. Do you talk to your guys on the floor? Do they clean up at the end of the day? Do they, have proper handling in place? Do they go back and do design reviews at different stages?
So we do have a member of our staff that is on the 217 handbook committee. Right now, 217 is at 2 level. That was the last one that was updated back in 1994. There is a G that is stuck out there in limbo right now, which from our conversations with other people we deal with in DoD, the G will probably be bypassed if it ever goes to another level, and that will go to H. And that will probably be the first time that 217 addresses physics of failure. So anything that's really a 217, if you're 217 plus, what's the other one? All the other modifications of 217 that are out there are all still doing the number crunching, parts counting type systems that they use. So they're not addressing physics of failure from a physics-based approach. It's always a statistical approach that they're using.
It's just as Tom said, it's a statistical approach with a lot of that. I know that in G, I know talking to our coworker Jim McLeish, who was on that working committee, they tried to include some photo type devices, some other optical devices, and when any mention of physics of failure was brought up, it was kind of just benched. So while they tried to do some updates on some of the tables for, say, smaller packaged ceramic capacitors, or a microprocessor that has a bit space higher than 8-bit. So we've got 32-bit architecture, 64-bit architecture, 128-bit architecture nowadays. 217 doesn't account for any of that because of the age of the data.
Okay, a couple more questions. Anastasio, how much time would it take to run one complex device, and was it not clear to me if the analysis is only for the intrinsic defects?
Okay. The tool as it currently sits is for intrinsic defects only, so it looks at those 4 failure mechanisms: dielectric breakdown, electromigration, hot carrier effects, and negative bias temperature and stability. We are in that kind of scope of work area of phase 3, where we are working on getting it into Sherlock as a module, but at the same time having it behave as a standalone tool. So we can look at not just what happens on die, but also look at the properties of the die attached to the package, what type of wire bonds you have within there, aluminum versus copper versus gold, how it's attached to the board, and what within the board, just beneath the components, may do to the IC itself. It's more of a little, an all-in-one model, so to speak. I call it the 2-inch by 2-inch square with an IC on top of it in realistic form, so we can actually address everything that's got to do with that IC. That is not fully produced right now, but we are headed in that direction to have that available. As far as the time it takes to do an assessment, it really depends on how much information you have on hand. If you just have a data sheet and you have an idea of what your field conditions are going to be, then it could take you 15 minutes, 20 minutes. If you have more information about it and how you're going to use the device, it could take you a few hours. And if you want to use data from a test, you've got to do the test first before you can plug the data in. And like I said before, we want to do a 2,500-hour test. You're looking at about 3 to 4 months worth of testing information, and then you've got to crunch those numbers. I like to set up our tests that are all in one, so the numbers are crunched for us, and then apply that to the algorithm. So it's always about what level of insight you have into the device itself and how you're going to use it.
Okay, a quick follow-up question from Ki Lu. For ESD, do you test to failure?
Well, for ESD, if we're going to do testing for ESD itself, so electrostatic discharge, a lot of the times what we'll do is just do a pass-fail after function test. So whatever the part's rated to, hit it with an ESD pulse that you control for pulse width, pulse height, and amount of energy present at what pin. And then what you'd have to do is you'd have to do a statistically sound set of those, whether that's 10 or 11 parts or 30 parts, and then you'd have to actually go through and do some FA on those parts. So some failure analysis, some decapsulation, and die inspection to see where, if any, ESD hit. So a lot of the times it can get out of those protection diodes and things, and you want to see if it did cause damage. And if it didn't and you don't see any, you may want to take a set of those devices that you hit with pulses and then actually put those through a maybe 168-hour test where it checks functionality to see if any of your parameters of your device has changed.
Okay, one last question from our Chalpo. Can this technique yield a failure rate for midlife, i.e. for IEC 61508 type modeling?
If I'm familiar with that question, then I'd say yes. This looks at midlife, so that bottom flat portion of the bathtub curve, and it also looks at the wear-out portion of the bathtub curve. So far, and not yet, I don't think anybody has actually hit this one on the head correctly, but the infant mortality portion, people have started to assess that region, but it's quite difficult because a lot of that's due to human-related defects. We induce something in the manufacturing and build out of that device, and that's why it's going to fail. It's all defect-driven.
So with that, I'd like to wrap up the presentation today. As I said at the beginning, this was going to be a very fast-paced, lots of slides. And as I've answered a couple of questions, yes, the slides will be posted. You'll get an email that will tell you where to go for the link. Not only the slides, the presentation itself will be posted on our website. So I thank everybody for attending. If you have friends that you would like to attend, I think we have some room for our afternoon presentation, which starts at 2 o'clock this afternoon, our time. If you have the registration link, give it to them, and they can register for the presentation. So with that, I'd like to thank Ed for all the knowledge he imparted here today. And I say, wow, there's lots of it. And thank you for attending today. And good afternoon.